All right. So last week when we were on Schoology, we learned about the law of conservation, and you were asked to do several discussion board posts. Just like we learned about the law of conservation for mass and matter, it's the same thing for energy. Energy cannot be created or destroyed, but we know it can be transformed. It can change from one type of energy to another, and it can be transferred. It can go from one object to another object. All right? So I asked you a series of questions last week, and one of the things I asked you is, can we account for all the energy in the golf ball drop? Yes, due to the law of conservation, we can account for all the energy in every system. Okay? And then one of the other questions I asked you, okay, had to do with this total energy equation. So we know that all energy can be categorized as either PE or KE. Why then is heat separated in that equation? Because heat is a type of KE. What happens when we add heat to molecules? What do? Move faster. Exactly, they move faster. So heat is a type of KE. Why then don't we just put TE is equal to PE plus KE? Why do we separate the heat? What happens to the heat? It doesn't go away, it gets away, right? Good though. It gets away. Heat escapes. Heat cannot be contained. When you turn your heat on in the wintertime, does it just come on once and your house stays hot all winter? No, it comes on a lot of times every day, right? Because that heat inside the house is escaping. So we have to be able to account for that. Because in every system, heat will escape. Where is that heat coming from in systems? Excellent. Friction. Now, friction is not a type of energy. It's a force. Excellent, Jai. It's a force. Okay? And it's a force that requires objects to touch. They have to be in direct contact. And when that contact occurs, some of the energy from that system transforms into heat. And then that heat escapes from the system. Every single system has friction. Every single one. There is no such thing on Earth as a frictionless system. So that means every single system will have some of its energy transformed into heat. Every time. Remember, there were two places in the golf ball drop where we had energy transformed into heat. Where was the first time? So I picked the ball up, held it. Where was the first time that some of that energy transformed into heat? When it was going down, because it was hitting the air molecules. All the way down, creating some heat, right? Transforming some of that energy into heat. And then when did the rest of it transform into heat? When it hit the sand and stopped. The rest of that energy was transformed into heat. So every system will have friction, which means every system will have some of its energy transformed into heat, which means every system will have energy that escapes. It's not destroyed. It just gets away. It can still be accounted for because it was not destroyed. It just got away. It escaped. Okay? Now again, this is all going to be on your Schoology. It already is, but now it's all together in one note session. Okay? So why won't the beginning energy of a system ever really equal the end energy? In other words, if I go to the gas station and I put gas into my car, does all of the energy, all of that stored chemical energy in the gasoline, does it go to just driving my car down the road? Where is some of that energy going?
The air.
Heat. Transferred to the air, right? Can you tell if somebody's driven a car recently?
Yeah. You smell the gas.
The hood is hot. Good, Amanda. From that heat, from the parts of the engine rubbing together and transforming energy into heat from the friction. Where's another place in the car where you have friction? The tires, where they're touching the road, right? So again, not all the energy from the gasoline is going into moving the car. Some of it is escaping in the form of heat. What this means is that there isn't going to be a system that will be 100% efficient. There's no such thing as a system where all the energy that is put in is used to operate that system. Because some of that energy will always escape in the form of heat. Okay? So that is why the beginning energy won't ever equal the end energy of a system. Okay? No system will ever be 100% efficient. This is why when you're looking at car, especially on commercials, they tell you about the difference in gas mileage. Right? Some cars get really good gas mileage. Others don't. That's because some cars have less friction than others due to mass, due to the shape, okay? Due to the size of the engine, all right? Okay, now we also learned that we can account for energy using energy chains. Some of you are really creative. We know I can't draw. That's been established. I'm a terrible artist. So I don't really draw pictures when I do energy chains. You may, okay? Use your creative side. Use your flavor. But it's the words in the energy chain that are the most important, okay? So the energy chain is a map of what happened. And this is the energy chain that I drew for the golf ball drop. Remember we said that the original energy in the system, okay, we know it all comes from the sun, but I'm not getting that picky. We said it started from the food energy, that stored chemical energy, that chemical potential energy in my body from the breakfast I ate. That then allowed me to transfer my energy to the ball and pick up the ball. So not only are you going to mark the transformations, the energy going from one type to another type on energy chains, you are also going to mark the transfers, the energy going from one object to another. So the first transfer was from me to the ball. Okay? And that transformation was from CPE, chemical potential energy, to GPE, gravitational potential energy. Because now that ball's height, its position in the system, will allow the force of gravity to make it move. Okay? Then I dropped the ball. So that GPE transformed into KE and some heat. Good, good. From it hitting the air molecules. Then it hit the sand. And all of that KE transformed into heat. Okay? Now, the transfers started with me, went to the ball. Some went to the air. The rest to the sand, then to the air again. Okay? And again, this will be online for you to look at as an example. Tonight's homework, the bottom 6 problems require you to draw energy chains. Now, you don't have to get crazy with it. There's not that much room. So let me show you an example of what the energy chain, if I did it on tonight's homework, would look like for the golf ball drop. I'm just going to account for energy transformations on tonight's homework. So here is what your homework problem would look like if I asked you to draw the energy chain for the golf ball drop. We started with chemical potential energy, which then transformed into gravitational potential energy, which then transformed into kinetic energy. Some of that was then transformed into some heat. And then all of it ends up being heat at the end. Every single energy chain you draw will have heat in it, right? We established that. But it won't always be the end product. It might be a little offshoot like this.